Alright, I'm going to show that C is infinite dimensional. Where C is a set of continuous functions. So I'm talking about functions here from the interval 0, 1 to r. So I'm going to suppose, to get a contradiction, that the dimension of C equals n, which in particular is finite. And then I'm going to use the following theorem. I'm going to scroll up here. To no linearly independent set of V contains more than n elements. So what I'm going to do is I'm going to find a linearly independent set. Right, maybe I should say this. If you have a linear space over the basis of n elements, like I'm assuming I have here, then no linearly independent set of V contains more than n elements. Well, I'm going to show that I have a set of n linearly independent of n plus 1 linearly independent elements that are linearly independent. I'm going to take x squared, x cubed, x n minus 1s. There are 1, 2, 3, n minus 1. So I need xn, and I'm going to throw in 1 as well. So these are functions. Remember, this 1 is a function. The graph of the function just looks like that. And I'm going to show that this is a linearly independent set. And the way I do that is I suppose C1x plus z plus cn xn plus cn plus 1, 1 equals 0. So what I can do is this is 0 as a function, by the way. This is not the 0 number. This is a 0. This is a function whose graph is that. What I can do is evaluate at x equals 0. And I'm going to evaluate at x equals 0. Notice that all these disappear, and I'm just left with cn plus 1 times 1 is equal to, plug in x into the 0 function, you get 0. So I get that cn plus 1 equals 0. Great. What I can do then is I can also, both sides of this equation are differentiable. So if I apply the derivative of both sides, what I get is I get c1 plus 2c2x plus that plus ncn x to the n minus 1 plus 0 equals the derivative of 0, 0. Now I can evaluate both sides at x equals 0 again. And now it'll give me c1 on that side, and now it'll give me 0. So c1 has to equal 0. Well, I can play this game all day. I can take the second derivative of both sides, and that's going to give me, once I evaluate at 0, the second derivative of both sides are going to be 2c2 plus, I don't know, 6c3x plus plus n minus 1 cn x to the n minus 2 plus 0 is equal to 0 because the second derivative. Evaluate at 0 and I get 2 equals 0. c2 equals 0. So I can just continue this process. So I get that the last thing is 0, then I get first thing is 0, third thing is 0, the third derivative will give me c3 equals 0, and the nth derivative will give me the last one 0. So in other words, I can continue this process and I'll get that all the coefficients are 0. But if all the coefficients are 0, this is a linearly independent set. Since this is a linearly independent set, it has n plus 1 elements in there, I couldn't have had dimension n by this theorem up here. No linearly independent set contains more than n elements if you have a basis of n elements. In other words, if the dimension's n. But here I haven't, the dimension here, there are n plus 1 linearly independent elements, so I can't have dimension n. So that must have been a bad assumption. So I can't have dimension n for any n, because I just keep repeating the same argument. If that can't happen for any n, I can't have a finite dimensional space. So it has to be infinite dimensional. And what we've done is we've shown that C is infinite dimensional. Because when I assume that it's finite dimensional, I contradict the previous theorem. Thank you.